Another application of the integral is hydrostatic pressure, or the pressure of water at rest. You can kind of think about it. Everyone's been toward the bottom of a pool and you're feeling all this pressure in your ears. So let's just kind of think about this as far as the force that that water is having on a dam. We're going to go ahead and let's see if we can kind of reason our way through this formula that we're given. If we take that slice, then let's think about the factors that are affecting how much force is on that particular slice in the dam. Well, of course, the density of whatever liquid is right there that's holding back. So usually a dam is going to be water, but that density is going to affect it. So we have our density here. Another thing is gravity. Gravity is pushing all of that water down. So, of course, we have gravity. How deep that slice is. So that's the A minus Y. And you can see that in the picture here. Toward the bottom of the dam, you can kind of think, yeah, that makes sense, right? There's a lot of pressure toward the bottom of the dam versus at the top of the dam. And that's why dams are built having a thicker base than they are at the top, is because there's more pressure at the bottom. So definitely that distance, how far from the top that slice you're looking at is going to affect things. And then, of course, the width of the dam. If you just have a dam that's very narrow, it's not holding back a lot of water, there's not a lot of pressure on it, so the force, the total force on the dam is not going to be as high. And then we're going to have a function of the width. This width function typically, not always, but typically is going to vary from the top to the bottom. It's going to be different. So that's why we're calling it a width function. Let's look at an example problem of the force on a dam. So we want to find the total force on the face of a dam when the reservoir is full. What it's telling us about this dam is it's giving us some dimensions. So it's telling us we've got a symmetric trapezoid. It's got a height of 30. So I'm just going to say that's 30. It's got a width of 20 meters at the base. So I'm going to say if it's 20 meters at the base, I'm going to say, I'm just going to go ahead and put that point out there. It's 10, 0 out there because we've got a total width of 20. So this is negative 10. At the base it's 20 and at the width it's actually 40. So if we come over here, I might go off the page a little on that side. But if I come over here, if the total width is 40 meters at the top there, then this half is going to be x is 20 and then our height was 30. Let's think about the slice we need. We need a width function. And when things are symmetric, I usually find it's easier to go ahead and just take a slice on one side and realize this isn't my total width function. This is my width divided by 2. But if I can find that, then I can find my width because I'm just going to multiply it by 2 to find my total width function. In order to find that, I'm going to have to come up with an equation for this line right there. Let's go ahead and first let's figure out our slope. Slope is the change of y over the change of x, or we could say it's y2 minus y1 over x2 minus x1, however you want to think about it. So we've got 30 minus 0 over 20 minus 10, so we've got 30 over 10. In other words, our slope is 3. I know a lot of my students, they like to use the y equals mx plus b. Sometimes it's a little more work, but it's not too bad. All right, y equals mx plus b. So we just need to figure out our b value. If I use 10, 0, then I can go ahead and plug in. I have 0 for y. I have 10 for x, which means my b is negative 30. I now have an equation for this line, which is just 3x minus 30. I do have a problem though, because look at that slice I did, my green slice. The thickness is going to be in terms of y. So I need my equation also to be in terms of y, which means I've got to go ahead and solve for x. So I'm going to say, okay, y plus 30 divided by 3 equals x, or x equals 1/3 y plus 10, which means my width function divided by 2 is just going to be, well, how far out does that go? That goes all the way out to x equals 1/3 y plus 10. If I multiply both sides by 2, I get 2/3 y plus 20. And let's use all this information we've got and let's plug it into our formula with the integral. My work equals, let's figure out our slices, where they're going from. What's the lowest my slice can be? Down there at y equals 0. What's the highest my slice is going to be? Up there at y equals 30. If you remember, I have density. The density of water is 1,000. I have gravity working on this, which is 9.8. I need to figure out my height function. How far away from the top is that slice? Well, if this is 30 and this is y, then the distance between those two is just 30 minus y. And then I have my width function, which we already found was 2/3 y plus 20 dy. All right, so now what I've got is I've got a constant here. I can multiply those together and I can pull them out in front of the integral just to make things a little bit easier for me. So I'm going from 0 to 30. And then let's look in here. Well, that's not really a form I can just go ahead and find the antiderivative of. So what I'm going to have to do is I'm just going to have to expand that out. I get, well, 30 times 2/3 y, that was that guy, plus 600 minus 2/3 y squared minus 20y, and it's still dy. 3 goes into 30 10 times. 10 times 2 is 20. Let's just rewrite that. It's a little messy right there. So we have 20y plus 600 minus 2/3 y squared minus 20y, and that's dy. And let's see what happens. My 20y minus 20y goes away. And so things are simplifying really nicely for me. So I get 600 minus 2/3 y squared dy. So we get 9,800. And then I'm going to find the antiderivative and evaluate. Well, I get 600y minus 2/3 y cubed divided by 3. And I'm going to evaluate from 0 to 30. 9,800 times, so I'm going to plug in 30, and I get 600 times 30 minus, and I get 2 times 30 cubed over 9. And then I'm going to go ahead and I'm going to subtract. Well, when I evaluate at y equals 0, I just get 0. And so instead of just going through the whole mess, simplifying this and everything, I know I'm just going to plug this into a calculator. It's going to be a huge number. It's going to go into scientific notation. So I'm going to go ahead and do that and just plug it in the calculator, and I get 1.18 times 10 to the 8th. And force is in newtons.